Okay, today's lecture is about LP spaces. So we're going to spend essentially 2 classes on this. This is a very important example of functional space, and this is kind of the beginning of functional analysis. All right, so we already saw L1 space. Remember, those are integrable function for a measure space XMU, and those were the ones that was integral of the absolute value of f, smaller or finite. Now we are looking at LP spaces for p between 1 and infinity, and we'll see later that we're going to make sense also of the case p equals infinity. And those are functions, measurable functions, that when you integrate, the integral of the pth power of the absolute value is finite. All right. Now, turns out that these spaces are nice. They're actually Banach spaces. In the case of L2, L2 is a Hilbert space. It's the only p for which p equals 2 is the only p for which the space is a Hilbert space. All the others are Banach spaces, and we're going to see what the jewel of these spaces are. Turns out they're reflexive. An easy observation is that they're actually vector spaces before saying they're complete, they have a norm, etc. So it's easy to see the vector spaces. Why? See, if I take a linear combination of f and g in LP, then you obviously have the inequality like this, just by using the absolute value, and then the pth power. If you think about it, this is an application of Jensen's inequality we saw last class. Just put the 2 here. It's the average between f and 2. 1/2, 1/2 at the pth power. This is smaller than putting the pth power inside. And this is what you get. All right, that's for p bigger, p bigger or equal to 1. This doesn't work. This is an inequality if p is smaller than 1. So you don't have a vector space if p is smaller than 1. This is the reason why we restrict to these p's. Right, and you have a norm for f, and this norm is the integral of fp. 1 over p, you need this 1 over p so that if you multiply f by a scalar a real number, then the norm of af is 8 times the so right, a norm should behave this way, and we should have a triangle inequality. So we don't actually have a triangle inequality also if p is smaller than 1. So that's another reason why we don't take these. Okay, so the triangle inequality we'll see a bit further down. This is called the Minkowski Inequality in the case of LP spaces. Okay? All right. This triangle inequality, the Minkowski inequality, we'll prove using Hölder's inequality, which is a bit of a generalization of Cauchy-Schwarz inequality. Great. Okay, so what about p equals to infinity? This is an important case. And this is the case where this essentially you take the suit norm. But since we're working with measures, it's a bit more subtle than that. We're talking about functions that are not bounded, but that are essentially bounded. That means if I look at the essential supremum, so this is the largest, the minimal c, all right, such that the measure of points such that my functions are bigger than c is 0. All right, so we do accept the fact that there might be a set of measures 0 whose value might be quite large, but on a set of full measure, the function is bounded. Okay, so those functions are essentially bounded, and this is L infinity. All right, so we're going to see many inequalities, well, 2 inequalities to start, Minkowski's and Hölder's, and we're going to recall some other important inequalities. All right. Okay, so let's start with Hölder's inequality. it says the following. So I take P again between 1 and infinity, okay, maybe equality, and I have the reciprocal of, well, the conjugate, sorry, of P, which is defined by 1 over P plus 1 over Q is equal to 1. This is very important. One over P plus 1 over Q equals to 1. So the conjugate of P is Q with this relation. If P is equal to infinity, then the conjugate is 1, and vice versa. All right? And Minkowski's inequality, Hölder's inequality tells you that the L1 norm of Fg is smaller or equal to the LP norm of F times the LQ norm of G. Okay? So in particular, if F is an LP and G is an LQ, so F is finite, G is finite, then F times G is an L1. Okay, so you get some statement about the product of these two functions. All right. Now we do the proof here for the case where none of the P or Q are infinity. If you are infinity, it's just taking the essential supremum out, and since the integral doesn't care about sets of measure 0, you get your result. Okay, and you can assume also. Okay, so this proves that. Now, in the case where P is strictly bigger than 1 and strictly smaller than infinity, you can always assume that F is finite and G is finite. Their norm is all finite, otherwise there's nothing to prove, there's no content. Alright, and the key point for Hölder's is just a lift of Young's inequality, which says that xp over p plus yq over q is bigger or equal to xy. Now notice that if p is equal to 2 and q is equal to 2, this is easy to prove. This is also easy to prove if p is not equal to 2. And my favorite way to prove this is using Jensen's inequality. So how do I do this? Well, take the log on both sides. Now the log is concave, so the log of this is bigger or equal than taking the log inside the integral. So now what's the integral here? Well, look, this is just a function on 2 points, and I take the measure which is 1 over p on x and 1 over q on x, and I take the function which is xp on x and yq on y. Okay? So that's a probability space that has only 2 points, and the measure is 1, because 1 over p plus 1 over q is equal to 1. Therefore, I can apply Jensen's inequality, and it goes this way because the log is concave. And now, if I take the log of the function, then I get p log x for x, but the measure of x is 1 over p, so the p cancels. So I get log x plus log y, which is log of x times y. Okay? And you get your inequality, log is monotone. It's increasing. All right? So that's Young's inequality. And now you're done because you applied this with x is equal to this guy and g is equal to this guy. Note that I normalize, I can do that because I assume it's finite. If f is equal to 0, also the inequality is trivial, I should have said. And then you're done because you just do this and you integrate this side, and you get this, which is the equality you want to prove. All right. So again, this is a generalization of Hölder's inequality. A generalization of Cauchy-Schwarz inequality. In the case of p is equal to 2, then q has to be equal to 2, and you get that the norm of f times g is small equal to the norm of f times the norm of g. Okay? So that's the first hint that L2 actually has an inner product, and the inner product is the following. So the inner product between f and g in L2 is the integral of f times g d mu. Okay? All right. We'll go back to that later. Now, the triangle inequality is called Minkowski's inequality for LP spaces. And here it is. So the norm of F plus G is smaller or equal than the norm of F plus the norm of G. Now, this is a simple consequence of Hölder's inequality. Here's why. Okay, so again, the case p equals to infinity I leave as an exercise, and the case p equal to 1 we already did. It's just linearity of the functions. Now, assume that p is strictly between 1 and infinity. Again, if f plus g is equals to 0, there's nothing to prove, so we'll be able to normalize by the norm by f plus g. So the non-trivial case is as follows. So now you just write the pth power of the LP norm. That's just this, and then you just separate f plus g into 2. So essentially you're using triangle inequality version 0, right? But then what you do, you have a product of functions, so you can apply Hölder's inequality to these. Okay, so you can apply it to here and here. And by applying it, you get the norm of f times this. Now you get q, all right, because you take the LQ norm. And same thing here. Now, because of the relation between P and Q, the conjugate relation, you get that QP minus Q is equal to P. Okay, and then so you're done. So you get that this quantity is F plus G to the power the LP norm of F plus G to the power P over Q. And if you divide both sides by this quantity, you're done. Okay, so you have LP spaces, you have Hölder's inequality and triangles inequality called the Minkowski's inequality. Okay, so very powerful. All right, so I recall here Jensen's inequality that we proved in an exercise like class. I also give the proof in terms of the thing is convex function as the convex envelope of linear function with the soup here. Okay, so I'll pass that. And I recall also Markov and Chebyshev's inequality here. You can look at this, and we've been using that. So I regrouped all the inequalities that we have so far: Minkowski, Hölder's, Chebyshev, Markov, and Jensen's. All right. Just a little thing I want to say here is that okay, we're going to show in the next section that LP spaces are complete. And the norm, I should say, so the norm that we define behaves like a norm. So if you actually see LP spaces as a space of equivalence class of function, why? Well, this is the usual identifications that two functions are equal if the equals on a set of full measure. So again, if the norm of f, the LP norm of f is 0, then that means this integral is equal to 0, and we know this is positive, so that means that f is equal to 0 mu almost everywhere. And therefore, the norm of f is 0 if and only if it is the 0 vector in my space, which is the function which is 0 almost everywhere. All right? So far we have all these inequalities. We know that also LP spaces are vector spaces, and they have a norm. And in the next sections, we're going to show that they're complete, and that's theorem 5. All right. Okay. Thank you.